Hey everybody, welcome back to another round of physics, and yeah, let's get going. I figured I would record a quick lecture just in case you wanted to go back and review of the problem that we did in class, and hopefully I can run it to completion as well, but let's take a gander here and see if we can figure that out. So the thing that we were dealing with, and let me set up the problem, we're going to start all the way from the beginning just so that we're all clear on what's going on. We had a situation. I said let us get a y-axis and an x-axis. Okay, so I'm thinking of x and y, and let's put some hash marks here. And we were saying that each hash mark represents a distance of 1 millimeter. Okay, first off. Now we put 3 charges, 1, 2, 3, 4, on this situation. Namely, I said this is a positive 3 charge, so 3 protons. Called this negative 2e, so like 2 electrons. And we put a positive 4e down here, so 4 protons. And the question we wanted to answer is, what is the net force acting on the third charge? Okay, so the 3e charge. And you could put in here due to the negative 2e and the 4e. In other words, using the negative 2 and 4 as the surroundings which influence the system. So this one's the system. Okay, now of course you're aware that forces obey the principle of superposition, and so we can think about the net force acting on our system as being the combination of the Coulomb force between the 3e charge and the negative 2e charge, and the Coulomb force between the 3e charge and the 4e charge. So I will go ahead, let's go through and figure out what the value is, how to calculate that force. And once we have the general process, then we can apply that general approach to find this one as well. Okay. So first off, focusing on just the Coulomb interaction between the 3e and the negative 2e charge, I'll go ahead and the first thing I'll write out is just Coulomb's law. It's always good to write out the general equation before substituting anything in. So I'm going to subscript that. For sake of argument, I'm lazy. I'm just going to call it 3, negative 2, and 4, referring to these 3 different charges. Okay? So that's just a notation that I'm going to use. So I'll call this the negative 2 charge. And reminding ourselves that in the denominator, that is the magnitude of the relative position vector pointing from the surrounding charge to the system charge. That is squared, and then of course we have the r hat sitting right there. Now the problem, we already have the charge values, the q's. We already know the constant, Coulomb constant K. So this problem, finding the force, boils down to determining what the relative position vector is. Okay. So let's go ahead and start thinking about that. First off, we have the position vector for the negative 2e charge. I'll go ahead and draw that in a ill-chosen green color. There. We'll make it nice and thick so that we can actually see it. Sorry, should have chosen a different color. Okay. That is the position vector of the negative 2e charge. Okay. So let's go ahead. First of all, what is the vector triplet for that position vector? Yeah, good. You see, it doesn't point in the horizontal direction, in the x direction at all. So the x component is 0, the y component is 4, good, and the z component, the out of page component, is 0. We're in the plane of the page. I'll go ahead and just for sake of argument, I'll remind ourselves that this is in millimeters. Good. How about the position vector for the 3E charge? Yeah, good. I assume that you have the right idea here. Pause it if you don't. But starting at the origin, we have to walk -3 steps, 3 units in the negative x direction, 0 in the y, 0 in the z. Okay. Good. Now, I guess for sake of argument, I'll do that one in green as well. Now, the question is, I'm not interested in the position of the -2e charge. I'm not interested in the position of the 3e charge. What I am interested in is the vector that points from our surrounding charge, -2e, to the 3e charge, the one that I'm doing in blue. Now, take a minute, convince yourself that this works. Okay? But you see now that I have done a tip-to-tail vector addition right there in my circle. Namely, I have taken the position vector of the -2e charge. I add to it the relative position of the 2e charge to the 3e charge. And that should result in the position of the 3e charge. Now, I can simply work my algebra. The fact that these are vectors, it still obeys our regular rules of algebra. And so I'll just move that to the other side, like that. And I get that the relative position vector pointing from the negative charge to the positive one is the position vector of 3e minus the position vector of the -2e. Well, we have numbers for that right here. So we can go ahead and plug that in. We end up with something that tells us -2, 3 equals -3, 0, 0 minus 0, 4, 0. And now we have to remember our algebraic rules for vector addition. Namely, that when we're dealing with the vector triplets, how we add vectors is doing it by components. This is completely analogous to doing the tip-to-tail method for geometric manipulations. Okay? So what we end up with here is, excuse me, I lost my cursor. There it is. We end up here is -3, -4, 0. And just for sake of completeness, I'll put in that this is still in millimeters. Now that should make some sense. If I were standing at the location of the 2e charge, what would I have to do to arrive at the location of the 3e charge? Well, first of all, I would have to go down 4 steps, and now I'm back at the origin. And then I would have to walk -3 steps in the 3 steps in the negative x direction. So it's always good to have a figure just to convince yourself that, yeah, the algebraic representation matches my expectations from the figure. Good. Okay. Well, now that we have the relative position vector that points from the charge to the system, we can go ahead and find the magnitude of that vector. And so it's always good to remind ourselves, how do we find the magnitude of vectors? So you should be thinking something analogous to the Pythagorean theorem. We take each of the components and square them and add the components together. And we have to take the square root of that. Square root. Now, of course, I've conveniently chosen a vector triplet, but the fact that the numbers work out to be nice and round, you know how to approach this, regardless of how ugly the numbers could be. Okay. So at the end of the day, we get that the magnitude of this relative position vector is 5 millimeters. Okay. Good. Now we have everything that we need in order to calculate the magnitude of the Coulomb force. Let's go ahead and get the unit vector that describes the direction. In other words, we should figure out what this vector is. Okay? The unit vector of the relative position vector. Of course, we remind ourselves that calculating this is simply scaling the original vector by its magnitude. And fortunately for us, we already have both of these pieces of information. We have the magnitude, which is 1/5, and I'll leave the millimeters in here just to remind ourselves. And we also have the vector triplet, also in millimeters. And here, we won't have to worry about the unit conversion. We have millimeters in the denominator, millimeters in the numerator, and so those units cancel out. And we are left with a unit vector that is -3/5, -4/5, and 0. Now, it's always good to check. If you're unsure of whether you've done the calculation correctly, just go ahead and check to see if the magnitude of this vector is 1. I'll leave that as an exercise for you. So now let's put everything together. We said that the Coulomb force between these two charges is KQ and we're now in a position where we can substitute in everything should we so choose. So I had I'll go ahead and write out this 1.6 times 10 to the -19th, since I have unlimited board space. You write this out enough and then you realize why you start getting lazy. I'll be careful right here. Okay? Now, up until this point, we have that the magnitude is 5 millimeters. Okay? But the Coulomb constant, the K, is in units of meters. This is always good practice when you're faced with several different types of units. Frankly, it's good practice to convert everything over back into SI first. Okay? But we remind ourselves, and that's a good practice just so you don't forget to do it later. Okay? So we'll go ahead. This is 5 millimeters, so it's 5 times 10 to the -3rd, and that entire quantity is squared. And then lastly, we'll include the unit vector, -3/5, -4/5, and 0. Okay. Well, now we're left with just doing the multiplication. Okay. Of course, we have 10 to the 9th, that would make it 10 to the -10th, 10 to the -29th, and then 10 to the -23rd. So we get something that says 10 to the -23rd. Okay. 9 times 2 times 3, that's 54. Okay. And let's see, we have a 1.6 and a 1.6, so that is 2.54. And lastly, of course, we have the 5 squared in the denominator, so we have 25. Okay. Bearing in mind we already did the unit conversion. Okay. And then lastly, we still have, you should yell at me. Oh, good gravy, I forgot the negative sign. That's a -2 charge. So there's a negative sign out front. Okay. And what I'll do is I'll incorporate that negative sign and I'll move it and I'll incorporate it into the unit vector. So we'll say this is 3/5, 4/5, and 0. Nobody noticed that slight indiscretion. Sorry. Well, yeah, I guess we just do it. right? What I'll do is let me scoot. I'm doing this in my head, so let's do it this way. I'm just going to scoot that decimal over 1. So you could think of this as being 554 times 25.4 times 10 to the negative 1 times 10 to the negative 23, okay, divided by 25. And I'll just say 25 divided by 25. Right? Sneaky. Okay. And of course we have the 3/5 and the 4/5 and the 0. So at the end of the day, we get something like 5.4. So I'm incorporating that 10 to the negative 1 with the 54. You get something like 5.4 times 10 to the negative 23rd. Okay. And that, you notice that this piece in the square brackets, that's the magnitude of this force. And then the direction that the force is pointing is 3/5, 4/5, and 0. Now you say, Greg, I want to know the x component of that force. That's perfectly fine. You have a scalar being multiplied, or excuse me, you have a vector that's being multiplied by a scalar. You can think of just distributing that scalar into each of those components, and that would give you the x component, the y component, and the z component. Good so far? Yeah, good. Why don't you go ahead, pause the video for a moment, see if you can follow that procedure to find the vector force between the 3e charge and the 4e charge. Got it? Yeah, let's go ahead and find that now. Okay. Well, and I'll remind you, the 4e charge from our figure here, we see that the position vector for that 4e charge is 0, negative 4, 0 millimeters. Okay. So we'll use that idea. So the first thing is we recognize that we need the relative position vector between those two charges. We can do the same song and dance and realize that it is the position vector of the third charge minus the position vector of the fourth charge. And here we recognize the third charge is located at, there we go, from the first part of the problem. From the second part of the problem, we have 0, negative 4, and 0. And so we get for this piece that the relative position vector pointing from the 4e charge to the 3e charge is simply negative 3, positive 4, and 0. Okay. That should make some sense. We're below the origin. So the first thing we have to do is walk back up to the origin, 4 steps, 1, 2, 3, 4, and then walk in the negative x direction, 1, 2, 3. Okay. Well, Greg, I already know, I'll put the units here, excuse me. And you say, well, I already know what the magnitude of this vector is. Turns out to be the exact same thing, 5 millimeters. Which means we can immediately calculate the unit vector between those two using those two ideas. And we get that the unit vector for this second situation is negative 3/5, 4/5, and 0. Now you can start seeing where some of the differences come in. The fact that the 4e charge is below the origin means that we have different signs on the components of the unit vector. If we go back and look the other time for the other situation, you notice that both of the terms when we calculated out our unit vector had negative signs with them. Here you can see that it doesn't matter what else is going on, we won't have the same sign for both of those components. So already that's how some of the math takes into account that one charge was above the origin and one charge was below. Well, now we have all of the information necessary to calculate the Coulomb force between the 3e charge and the 4e charge. Namely, I'll go ahead. Again, I've already told you, it is good to write out the general equation. Essentially, you are stating your starting point before you substitute in numbers. And we can go the same, keep going, right? We have a 9, 10 to the 9th. We have 3, we have a 4, and I'll go ahead and I'm going to lump stuff together now because I am incredibly, that's right, lazy. Lazy, lazy, lazy. Times 10 to the negative 3rd squared. And I'll go ahead and put in my unit vector. Okay. Now, if you're following along, yeah, go ahead. You can go ahead and find the stuff. 9th, negative 38th. So that gets us to like, what, the negative 28th? 38th, 29th, excuse me, 29th, and then you got a negative 6. So we're still, and that shouldn't be a surprise, we're still at 10 to the negative 23rd. Okay. And again, we use that little trick. We said 3, 4, and 9. So 9 times 12, 108. Okay, so that's 9 times 12. And then we have that 2.56. That's the 1.6 squared is 2.56. Divided by 25. Oh, excuse me, not equals. I'll put the direction in here. And the same thing, I'll pretend that I move a decimal here, and I'll take that decimal and move it there. So, if you will, transferring kind of a power of 10 from one of the numbers to the other. And I'll just ballpark and say 25 divided by 25 is basically 1. So I'm going to get something that's approximately 10.8 times 10 to the negative 23rd, negative 3/4, 4/5, and 0. Now, one of the things I should notice, okay, one of the things I'll point out to you, notice how this one points not in the first quadrant, right? The past problem, I should highlight, positive x direction, positive y direction. So it points, this force is pointing towards the first quadrant. Here, we have a negative x component, so negative x component, and a positive y component. So instead of it pointing in the first quadrant, it is actually pointing in the second quadrant. That is the quadrant that consists of negative x's and positive y's. So they're in different directions. Good. All right. Well, last but not least, okay, we are asked to find the net force. Now we have found the force between the 3 and the negative 2. We have found the force between the 3 and the 4. The only thing that's left for us to do is add the forces together by components. And that will give us the net force. So again, the net force is the force between the negative 2 and the 3, and the force between the 3 and the 4. Okay. Well, for the first one, I apologize, I've already forgotten, 5.4. So for this first one, we had 5.4 times 10 to the negative 23rd times 3/5, 4/5, 0. And then we had 10.8 times 10 to the negative 23rd. It's nice that we have the same kind of factors floating around, isn't it? It'll make our lives a little bit easier. We have 3/5, 4/5, and 0. And the negative sign, remember we said it was a negative x. Okay. So let's go ahead. Let's add by components. And you notice we have a common factor of 3/5 and 10 to the negative 23rd. So if I add the x components of these, I get 5.4, I have 10 to the 8th, and notice again, there's that negative sign. Okay? So I should be careful there. We always, I emphasize negative signs because I tend to drop them. I tend to forget them. Okay? So I get 5.4 minus the 10.8 times 10 to the negative 23rd times 3/5. And again, this is taking into account that those forces are pointing, they have different signs for the x components. So there's the x component of the net force. I can similarly write 5.4. Now notice both have positive y values, so I get plus 10.8 times 10 to the negative 23rd times 4/5. And then 0. Well, that's it. We're done. I guess we could do the math, right? Like, and this is a negative 5.4 times 3/5. And then we have, what, 16.2 times 4/5 and 0. And I just pulled out that common 10 to the negative 23rd. There we go. There is the vector that represents the net force acting on our charge 3e. Now, you could probably, you did the exact same thing. You might have said, wait a minute, Greg, I prefer to do the triangles, right? I have a triangle that is 3 units in length and then 4 units tall. So here's my triangle. And then I find an angle, and then I define the cosine of that angle. I do the sine of that angle to break it into components. That's perfectly fine. Okay? Based on this problem, recollection is that angle there is something like 53.1 degrees. Okay? And now here's where those two approaches, they doesn't matter which one you do, but these two approaches come together. Okay? Go ahead, take a second. If I did the cosine of 53.1 degrees, what is that answer? Hopefully you got 3/5, right? You go, wait a minute, I've seen that 3/5. That 3/5, that was the x component stuff. Okay? And the same thing, if you did sine of 53 degrees, you should get the 4/5. Okay? So that's where the two problems come into play. Okay? I did everything in terms of leaving it, I did the relative position vectors, I did the magnitudes, and I left it in terms of vector notation. Okay? But that's completely synonymous with taking the triangles, finding the angles, doing the adjacent sides, doing the opposite sides. Okay? So it doesn't matter which way you approach it, they're both correct. Okay? I like doing it this way, partially because you need to get used to seeing vectors, and also this approach is helpful when we have more complicated distributions of charges. Okay? Oh, cool. Well, I'll leave it there. Yeah, that's all I have for this video, is just to try to recap and finish off the discussion from lecture, that kind of thing. Hopefully you find it helpful or useful to go back and review. So, hey, thanks for your attention. Keep up the good work. I'll see you next time.